Today, we're going to start our section titled Enthalpy of Reactions, and basically, this is going to be our stoichiometry part of this chapter. Remember, we learned stoichiometry at the very beginning of the first semester, and it's going to continuously be brought back up because it is the foundation of a lot of different things that we do in chemistry. So, as a little bit of introduction, we've talked about enthalpy, again, that's denoted by the letter H, as the heat or energy transfer for things that are generally under constant pressure. And a lot of people are like, well, Mrs. Grove, stands for Q. But in terms of when things are under constant pressure, Q is usually equal to your H value. So, similarly to what we see with Q, delta H, when it's positive, that means the system has either gained heat or energy from the surroundings, and so we call this endothermic. And again, when delta H is negative, that means it has released some kind of heat to the surroundings, and that's exothermic. So, in terms of that, we're going to go kind of through this little example and a couple things that I want to hit on. Oftentimes, you're going to see the problem be worded like this in the example. 2 moles of hydrogen gas burns to form 2 moles of water vapor, because it's in its gas form, at a constant pressure, and it's saying that this releases 483.6 kilojoules of heat. So you can write that in sentence format like we did up here, or you can write it in a chemical reaction. So here is my 2 moles of my H2 gas. It's going to burn, so it has to combine with oxygen. And again, it says form. So this arrow means that it's going to form or produce. Here's my 2 moles, and then here is my water vapor or my H2O in gaseous form. And then it says the system releases, so that's why I have a negative sign here, 483.6 kilojoules. Note that my delta H is a negative sign, so this tells me that this reaction is exothermic. And then I also want you to note that this delta H value has to go to this reaction. It does not specify explicitly the amounts of chemicals involved. So it doesn't tell you specifically that I had 15 grams of this or 5 grams of this. What tells me my numbers is my coefficients. If I look at that balanced equation, that coefficients represents the number of moles for reactants and products that are produced. So for example, if I was looking at H2, this reaction has negative 483.6 kilojoules per 2 moles because I have a coefficient 2 here. So that stands for my 2 moles. Whereas if I was doing oxygen, for every negative 483.6 kilojoules, that's for every 1 mole because my coefficient is 1. We tend to call these balanced chemical equations that have the delta H values with them thermochemical equations. So here we're going to go through 3 examples, and I'm going to kind of specify and talk about specific things. So here this question is asking how much heat is released when 4.5 grams of methane gas is burned in a constant pressure system. Down below, it gives me the chemical equation, and then it gives me my delta H value that is associated with it. Before you even start this problem, first make sure that what the words are saying actually matches up to what's happening in the equation. So for example, it says how much heat is released. So I know that I am going to have a negative value here. And then the other thing it says when methane gas is burned. So that means methane is one of my reactants. And that's going to be CH4. So down below, you should see CH4 to the left of your arrow, and it should show that it's going to burn. If that reaction is the same as what's stated above, this sign is going to stay negative. If the reaction is opposite, this sign is going to change to be positive. So if instead it said how much heat is gained when 4.5 grams of methane is formed, then you would flip the sign here in order to do the math that we're going to do coming up. So just like any stoichiometry, a problem, we always have to start with what we're given. And here we're going to see that we're given grams, and what we want to get to is how much heat. Well, heat is going to be in kilojoules. So I have to somehow get from grams to kilojoules. We always start with what we know, which was 4.5 grams of methane, so CH4. Again, whenever you're doing stoichiometry, your middleman is always going to be moles. So you always want to get to that mole value. In order to go from grams to moles, I have to find my molar mass. So here's my grams. I want to cancel it, so it goes on the bottom and moles on top. So remember, this is how many grams per 1 mole. So if I find the molar mass of methane, we have 1 carbon plus 4 hydrogen, and that gets me the molar mass of 16.04, 0426. But now I've canceled grams, I have moles. Again, remember, this is moles of CH4. I want to get to kilojoules. So in order to cancel moles, I have to put it opposite. So moles of CH4. But what allows me to go from moles to kilojoules? Well, what's going to allow us to do that is my balanced equation along with my delta H value. So I can put kilojoules here on top. So here, if I find CH4, it tells me for every 1 mole of CH4, because that's my coefficient, that is going to be equal to negative 890 kilojoules. So now I have canceled my grams, I have canceled my moles, and that leaves behind my kilojoules. I have found what I wanted, so then you can go ahead and plug this into your calculator. Remember, if you're on the bottom, you divide. If you are on the top, you're going to multiply. And you should get negative 249.6478127 kilojoules. But remember, sig figs. So here I have 3 sig figs. We use this number. This one has 2. So when I give my answer, I can only have 2 sig figs. So negative 200, and that 9 is going to round that 4 up. 250 kilojoules. So let's do another example with that. Here it says hydrogen peroxide can decompose to water and oxygen by the following reaction, and my delta H value is negative 196 kilojoules. So remember, our reaction should match. Otherwise, that we have to make sure that we flip our sign. So hydrogen peroxide, is it decomposing? Yes. Here's H2O2, my hydrogen peroxide, and it is breaking down. So here I want to calculate the heat released. So yes, it makes sense that this is a negative sign when H2O2 decomposes. And yes, it's decomposing. So let's start with what we know. 5 grams of H2O2. Again, your middleman is always going to be moles. So if I want to cancel this, grams of H2O2 are going to go on the bottom because they're opposite. Moles of H2O2 is going to go on the top. So here I have 2 hydrogen, and then I have 2 oxygens, and that gets me, for every 1 mole, my molar mass is, oops, that kind of looks like it's merging, so I'm going to write it down here just in case you guys cannot read what that says. So 34.0138 grams of H2O2. Then what we could do is we have it in moles now. We have to somehow cancel that moles and then get to kilojoules. Well, here, our kilojoules is negative 196, And well, if I go here, remember that kilojoules is always associated with the equation. So if I look at the equation and find H2O2, my coefficient is A2. Now I've canceled out grams, I've canceled out moles, and I just have to get to my kilojoules, and that's what I want. So you can take that 5 divided by that 34 times negative 196 and divide that by 2. And you're going to get negative 14.4059176. Again, we have to worry about sig figs, so this one has 3 and this one has 3. So my answer is going to have 3 sig figs, or negative 14.4 kilojoules. And then here is our last example. Please note that this one is different. Instead of going from grams to kilojoules, we are now going to be going the opposite way. So here it says the value of delta H for the reaction below is negative 482 kilojoules per mole. So it says the reaction below is that. So that means this is going to be associated with that equation. It's basically another way to state that your delta H equals negative 482 kilojoules. So we've taken what was written on the side over here on the last equation, and we have just put it in a sentence form. Oops. So if you want to rewrite it down here, you can. Our goal is to find how many grams of carbon dioxide is produced during an enthalpy change of negative 1067. Again, you always start with what you know. Negative 1067 kilojoules. With anything, if I want to cancel it, kilojoules is going to go on the bottom. And our middleman is always going to be moles. So remember, this is always going to go with our moles. And specifically, we're looking at moles of CO2. So when I look at this, my kilojoules value was negative 482. If I find CO2, I notice that my coefficient is a 2 for my 2 moles. That gets rid of my kilojoules, but now I have to somehow get from moles to grams. Remember, what allows you to go from moles to grams is molar mass. So if I have moles of CO2 and grams of CO2, I can just find that molar mass. That tells me I have 1 carbon and I have 2 oxygen. So if you calculate that, 44.009 grams. Remember, that's always for 1 mole. Now I've canceled out my kilojoules, I've canceled out my moles, and that leaves me with grams, so you can go ahead and solve. So negative 1067 times 2, because that's on top, divided by the negative 482 on the bottom, and then multiply that by the molar mass, and you get 194.8448257. Note here, my unit is grams of CO2. Don't forget about sig figs. Here, this has 3 sig figs, and this one has 4. So I should only have 3 in my answer, 190, and that 8 will round that 4 up to a 5. 195 grams. And don't forget to have your CO2 because that's part of your label. Because is it grams of CO2, is it grams of O2, or is it grams of CO? Make sure you guys are specific in your guys' answer. So here, this one's 195. Again, just before you guys log off, make sure that what happens is supposed to happen. This says CO2 is produced. Down here, you're seeing, yes, it is created because the arrow is showing that it's reacting and becoming that. So that makes sense. My sign makes sense. If you are struggling with this, please make sure that you guys reach out. Otherwise, I hope you guys have a great day, and let me know if you need anything.